actually do once you understand it, understand the content of the theorem is the following. If it goes to the same value, no matter what, why don't we choose the simplest partition and simplest choice of height points, right? They all go to the same value anyway, right? So what is the simplest one? Regular right Riemann sum. You don't have to choose a midpoint. Simplest one is formula-wise the simplest. Regular, choose right endpoint. Everything is simple. Then that regular right Riemann sum will approach whatever that L value was asserted to exist by the theorem of integrability of continuous functions. So we're going to focus on regular right Riemann sum, right? Okay. So here's a complete formula of the regular right Riemann sum. So I want you to figure out where that b minus a divided by n come from. Where did that come from? What is b minus a over n in terms of partition notation? Size of the partition, that interval length right there, right? Delta x, they're all same. It doesn't vary with k. So we can set outside linearity of this sigma notation. How about inside in here? F of is supposed to be xk star, right? This is supposed to be xk star, but we choose right Riemann sum, so this is just right endpoint, xk. And this is the formula of xk for regular partition. All right? So I want you to go and have a, chance to write this one completely down. You're going to just use all the time, not, for this class and the next class, to compute this definite integral. This is your exercise number 1. Everybody gets full 2 points. Just write this one down. If possible, do not look at it and try to write it down on your own in terms of A and B and K in a very, very explicit form. All right, how was it? Was it all right? This is delta x, f of xk star again. That's right endpoint of each interval. Any question about this formula? So whenever you're asked to compute the regular right Riemann sum, you write this one down as exactly like this verbatim and identify what your b and a and n is, and you're going to calculate the sum. All right? And what does this arrow mean? As n approaches infinity, right? Now once you have this formula ready, simplified, and send n to infinity, what's going to happen if that's 5 and that's your answer, definite integral being 5. All right? Any question? Let's look at this caution. It said this is not the definition. The definition of this definite integral had 2 things: wordy definition and precise definition. Under the limit, there's a p, partition varies, height of choice of height point, p star varies, and it goes to infinity. That's the definition, and this is a theorem that you can calculate that through this regular right Riemann sum. Right? I asked you to learn about this summation notation, and before I go into the summation notation, this is the picture of Riemann, student of Gauss, and who thought out this and decided to do it a little bit more carefully, and it's named after him is Riemann sum. How about this notation? I ask you to read about this notation and example 119 or something. So was there any question about understanding this notation? I'm going to do just one problem, which is part 2, and you might have read about it, but let's see. I'm going to explain a little bit, and if you have a question, you can ask a little bit. So here's AK is this formula. I don't like this I, so I'm going to write everything in terms of K. So how about this one? K going through 3 to 7, and inside we have 3AK minus 4, right? And they said AK has this formula, 2K minus 1, right? And they ask you to compute this value number 2. It's supposed to be actual number like 5. There's no A in it. There's no I in it. It's actual number. All right. Let's look at this one. AK is representing 2K minus 1, right? All the numbers 2K minus 1. If K is 1, A1 represent 2 times 1 minus 1, 1. A2, when K is 2, if it's 4 minus 1 is a 3, and so on. You plug in K, as you vary this k value, you have this value a subscript 1, a subscript 2, and so on. They ask you to compute this value. So what I'm going to do is I'm going to write this one down with that formula. K equals 3, and this is capital letter sigma, like that, and it ends at 3. So it's a case 3, 4, and 5, and 6, and 7, right? You have to add all those 5 numbers. 7 minus 3 is 4, but it didn't count k equals 3. I'd have to add one more, 5 numbers. So 3 times, what is AK? AK is this one here, right? 2k minus 1? Just 2k minus 1. And there's out there 4. This expression with k is hit by this operator, sigma, some operator, then it's going to be a number. So let me expand this one in here. You see that's a 6k if you distribute it, right? Minus 3 minus 4. So what do you see? K equals 3, 7, right? And 6k minus 7. Any question about this manipulation? Look at the inside the expression. Actually write it explicitly in terms of k. Any question? Now I'm about to use the property, something called linearity of the sum notation, right? As if it is a number, this is a symbol, right? Describing what to do about this formula. You can distribute it as if it is a number. You can put it on the left of that expression. You can also put that on the left of that expression, passing the negative, right? That is one part of the linearity. So I'm going to write it like this. K equals 3, 7, 6k there, right? Minus, this represents one quantity. You keep adding 6k when k equals 3 and k equals 7 and so on. Make sense? Right. How about this one in here? You pass that. K equals 3, k equals 7, and there's a 7, and this is another number. This manipulation makes sense? So this one says you keep adding this one 7 times, right? 7 times is added here. But they separated now. Do this one 7 times, to that one 7 times, and subtract from one another, and that's the answer. This is order of operation. Subtract first and add later, and add the sum ends later separately and subtract the whole thing later. Different order of operation is equivalent to distributing this operator, and especially over this linear operator. All right, so let me go on further. What can we do about this 6 that doesn't change at all as k vary from 3 to 7? Differential operator, integral operator, all linear operator has the same behavior. What can we do with the 6? You can put it outside the operator, right? So 6 goes outside. You can pull k outside. You got to leave it in there. K goes 3 to 7. And what is left here? K there, right? So this is like adding all those 3 plus 4 plus 5 plus 6 plus 7. That's what this one represents, right? And multiply by 6 later. And you can do that with the 7 too. And the 7 is pulled out. And k is going from 3 to 7. And here we're left with what is left outside? Inside, you have to factor out 7. Invisible 1, right? You keep adding this number with k equals 3 and 4. But you realize there's no k in there, right? All 1. So it's the same as adding 1 plus 1 plus 1 plus 1 all 5 times. Okay? So, what is this number? Let's write that down. First number, what is if you expand this one out as a sum of 5 numbers, what is the first number? 3 and plus 4 plus 5 plus 6 plus 7. That 5 number, right? Correct? How about this one? 7 times. 1 plus 1 plus 1 plus 1 plus 1, right? So how many? 5 of them. Whatever this number is, that is answer to this summation. So I use this example, just introduce this manipulation, which we have been doing with the differential operator, with integral operator, indefinite integral operator. We did that, 2 of them, right? So we're familiar with this phenomenon. Any question about this manipulation? Yes. Here, when you plug in I equals 3 and I equals 4, it does not replace the entire AI. It only replaces this 3 there and 4 there. Then you have to go back to the formula and replace that 2 times 3 minus 1 and replace with the number, right? That's probably what they want at this stage, right? But after that, they introduced this type of manipulation, so I introduced that more algebraic stuff using this example. But what you said is correct. Any other question? So they listed these properties, the summation property. Let's look at the first one. There's a c represented as a constant multiple. Constant. It's not changing, and as this parameter k changing from 1, 2, 3 to n is always a c. Then they're saying it's a c times n. Does that make sense? Because you're adding c, then adding c again, c plus c, and so on. You keep adding c, so n times c makes perfect sense. What is a good name to describe this property 2 and 3? This is precisely the property of what? 2 and 3. Differential operator, integral operator, indefinite integral operator share this property. What was that? It was a linearity. This operator is linear, so it distributes over this. This is like distributed over addition and subtraction. If you have constant multiple, you can set outside, and just to deal with what remaining part, these are the constant multiple. Let's look at number 4. Can somebody make sense out of this number 4? Pay attention to index. How is this index changes? From m to where? You see that? That's a j. Okay, j. M to j. Next one. From j plus 1 to n. Do they kind of lock each other perfectly? You go from m to j with this expression ai. Now, right after that, it starts from j plus 1 all the way up to n, right? So isn't that same as just going from m to n, straight? So that's what they written there. We have the same phenomenon in integral. A to b to c integral, and that's the same as a to c integral, right? So it's easy to understand. This 5 and 6 and 7 is not easy to understand, right? Once the great mathematician Gauss, when he was very young, this anecdote is available everywhere. He was challenged by his math teacher that to sum up these numbers up to 100 or something, so that students are working on this tedious work and teacher can do something else in his desk. But Gauss was able to do that really quickly. So this 5 and 6 and 7, we're going to go through it together. I'm not going to prove it. I don't think we have time for that. But it's very, very available these days. And it is an important fact in mathematics. It's true. It is very, very important fact to the foundation of the mathematics. But I find it's a bit too much. So not many formulas given in my test, right? Actually, no formula is given in my test except this 5 and 6. You'll be doing this problem that uses 5 and 6, and I'll give you that formula in 5 and 6. But as far as I know, students who practiced for the test ended up at memorizing this fact anyway, but it'll be given. Okay? So let's learn this formula. All right. So I'm going to change to k. Doesn't matter k or j, or I use k there. I'm going to use k going 1 through 10, for example, like that. Let's say 100, like going back to Gauss, period. Let's write this one out. What is the first term? 1, right? Second term? 2. Third term? 3. And go all the way up to consecutively, up to 99 and plus 100, right? Okay, so if you add them all that, what's going to happen? Do you know the answer? Answer is given to you right here, right? So what is the n value here right now for our problem? 100. So you plug in 100 there, times, what's the next number? 101, right? 101. Make sense? Divided all over 2. What is it? 50 times 101. Whatever that number is. If you add them all up, take several minutes or 20 minutes, whatever, and that's supposed to be the same as this number. All right, so you have a closed formula. You don't have to add all that 100. You just plug it in here. That's the answer. That's what this formula is about. Any question about the formula? So Gauss did it quickly. He didn't add up. Clever trick. Figure out that number. All right. So let's look at the second. Number's already big enough because you're squaring it. So I'm going to hold it to 10. K squared. What is the first term? 1 squared 1, right? Second term, 2 squared, better known as 4. Third one, 3 squared, better known as 9. If you keep doing that all the way up to 9 squared, 81, and plus 10 squared, which is 100. What's going to happen if I add all those up? Answer? Answer's written here, right? If you add the squares, what's going to happen? So what is our n value here this time? 10, right? Is it 10? So 10 times 11 times 21 divided by 6, right? 6 is 3 times 2. So 3 cancels with this 21, and 2 cancels with that 5, giving you this 5 times 11 times 7. You work that out. If you actually add the squares with your calculator, you realize that they are the same number. And you guarantee that whatever number n you put in there, that's the answer. Right? There's two formulas there, and they also show you the third power, and it exists in the internet, fourth power, and fifth power, and the entire formula is available now. Okay? So if you use the name Bernoulli, and you can enter this interesting facts. But these two will be given, and the problem that you're going to be dealing with in the test is using these two formulas. Okay? All right. So we better do some examples so that this makes more sense. All right. I think I did this example. I'm going to rewrite it with K. I'm going to do some part and leave the rest of the part to you. For this one, I'm not going to plug in k equals 1 and k equals 2 and 6. We're going to use that formula that I just showed you, right? This is going to be practice for that formula. 2k minus 1, if you plug in k equals 1, you just realize that's odd number, 1 and plus 3 plus 5 and so on, right? So when you look at this, suppose this is not 6, it's actually 66. Then you're not quite encouraged to plug in 66 times. Then what do? What property of this operator do we use? Distribution. Thank you. The linearity. So do you see this distributes like this? 2k, k equals 1 to 6, minus k equals 1 to 6, 1. Do you see that? This distributes over these two things, right? What is the next thing we do? Linearity. Bring the two outside. So that means you add this number up to 6 first, then at the end multiply 2. That's the difference. You multiply 2 to each of the sum end, and then add, versus add first and multiply 2 later. How about this one? This is pretty easy. Minus 6, right? 1 through. Make sure you count that one. So what is this one in here? K2, 3 to 77. What is this answer in here? This is not 77, right? It's missing how many terms? 2 terms, right? Is that 75? Because k equals 1 and k equals 2 is missing. 1 through 77 minus 2. Correct? Right. So this is 75. Make sure you pay attention to the beginning value as well. All right. Then this is 6. Right? So who remembers about this guy? Adding 1, 2, 3, 4, 5, 6. Remember formula? Don't worry. That'll be given. Remember? That'll be given. That formula will be given. So right there. N times n plus 1 divided by 2, right? So what is it? N times n plus 1 divided by 2, where n is 6. Love this notation. Here's a 6 times. So I dropped the term. There was negative 6 out there, right? You shouldn't drop that. And there is 2 out there as well, minus 6. How about that? Fair enough? Only that part was replaced by the formula. So you can see 2 cancels, right? So you leave the 2, 6 times 7, is that right? Minus 6. What is it? 36? 6 times 6, 36. All right. Any question? So I'm going to do next one. Why don't we just work this one out in general, like that? Any question? So we don't know what n is. We're just going to do this formula and write it as a function of n in there. So let's do that. Okay, so distribute n, 2k minus 1 through n and 1 in there, right? Fair enough? And pull out 2, and that's going to be 1 through n, k, so you work this one out, and minus, what's the answer to the second term? Just n, 1 times n, there. All right? So, who remembers the formula of this one? Adding 1 through n, all these consecutive integers. Don't worry, if you don't remember, this will be given. This is n times n plus 1 divided by 2. And n is just unknown like this. N minus n, right? And these two n's cancel. I mean, 2 cancels, right? So leaving n times n plus 1 minus n, right? So what's the answer? N squared. And n cancels, right? Great. And it cancels. Did you know that if you add odd numbers up to n, it becomes a perfect square? For example, if you do 1 and 3 and 5 and 7, what is the number? 10, 16, right? That's a perfect square, right? So that's what we just proved. If you had odd numbers up to whatever, it always became a perfect square. Cute fact, right? It's not over yet. Here's the actual one. Now, why did we all do all that? To calculate this guy, right? That's the whole, this section is about this symbol and the meaning. We draw a picture and use triangles, and we spend long time of dealing with this partition and all that thing just to compute this one with a bare amount of understanding, right? Okay, so this is definite integral, and there was a theorem of integrability of a continuous function allow you to compute this one using what Riemann sum? Right regular Riemann sum, right? Just compute that. So here is right regular Riemann sum. Who remembers this formula? This is not going to be given. You're supposed to remember this one. There's a sigma out there, right? K is going from 1 through n all the time. What's outside this sigma? B minus a divided by n. Thank you. What's inside here? Function f, right? But what's inside that function x? F? xk, right endpoint. How does xk look like? Right, x sub k, what's the formula? You started from a, right? Plus how many times you go to the right? K step. Each time you go this amount, right? Right, that's the formula. You write this one down every time you're asked to compute regular or right Riemann sum. Now you have to plug in the information. What are b and a here? Right, it's 1 and 4 here. So 3, right? Divided by n. This doesn't change. K1 for n. What about this one? Let's go work inside first. What's a? 1. K and n, I'm going to group it like this. How about b minus a? We worked it out 3, right? That's the formula. So what are you going to do with 1 plus 3k divided by n? You're going to plug that one into this formula right here, right? So let's do that. 3 over n big summation symbol. And it's a 4 times what? That whole thing, right? 1 plus 3k over n minus that whole thing is a squared there, right? So it's 1 plus 3k over n squared. Now you entered very explicit. Everything is k and n. There's no f, there's no star, anything. This is something you can compute, all right? And n is not changing, right, as k changes from 1 through n, correct? So it is considered as a constant as k changes from 1 through n. So let's work that out. 3 divided by n. So 4 is multiplied. There's a 4 there, right? About 12k divided by n. Is that okay? 12k divided by n. And minus, what happened if you square that? You have 1 squared, you have to square that. So it's a 9k squared divided by n squared, right? Do you know what's in the middle? 2 times this product of these two things. So therefore, it's a 6k divided by n, right? So simplify it further. There's no constant term in there. There is constant term. So they're together 3. Do you see that? 4 there and minus 1. Right? So it's 3. Do you see the same shape as 12k divided by n? Right, 12k divided by n is there. And this one with a negative, there's a 6k divided by n is there too. So together, 6k divided by n. So how about this one? Is there anything that like this one? K squared divided by n squared, that's it. So I'm going to write 9 times k squared divided by n squared, right? Alright, so that's simplified. What do you think our next step is if I write 3 over n set outside and try to do something about this summation? What do we do? Well, we're going to distribute first. You can't just take the 3 out and, leaving it on here. But 3 is a common factor, that is true. But I'm going to distribute the sigma first. So here's a sigma here. There are 3. And sigma goes there, right? Distribute it. 6k divided by n. And cross that, negative. And goes there. Is that right? Now what's the next step? Pull out all the constant. The 6 is constant there, right? 9 is constant. You can pull it outside of each of the sum. How about those n? Does n vary as k goes from 1 through n? It never varies. For whole thing, n is fixed and k is only varying from 1 through n and 1 through n. So this n is considered as relative constant in that sum. So you can pull out n as well. So 3 is pulled out. Plus, what is pulled out here? 6 is out there, right? And n is out there as well. And it's always there, never changing. So what's remaining here is a k, right? And you can see that, oh, I know what that is. Do you? Don't worry. This will be given. Remember? N times n plus 1 divided by 2? That's what that is. Adding 1, 2, 3, 4 all the way up to n, right? Okay. How about this one? What are you going to pull out? 9 and n in the denominator squared. Thank you. Then there's a k squared. K going from 1 through n. Do you know what this one is, adding 1 through n? Yeah, that'll be given. So we're going to replace that, right? And then expand it all out and try to simplify it as much as you can, right? That is the answer to what question? Regular right Riemann sum of that. That's not even yet the integral in here. That's right. That's the whole test is about this. Yes. It's just because the function requires 4x minus x squared. So you have to plug in everything into x is there. Right. Any question? Right. Right. But it's jagged, like that, all flattened out, not the perfect one. So this one looks like the function like that, but it is like this, not a perfect one. But if you keep chopping down, it becomes more and more some number, and that's the last thing we're going to do. All right, let's just stare at this and think about what to do. And what about this one in here? This is not going to be given. This is not going to be given. What is the answer to the first summation in here? N times 1, so therefore is n. How about the other one, 6 over n, this one in here? N times n plus 1 divided by 2, which will be given. 9 divided by n squared, right? How about this guy? N times n plus 1? 2n plus 1. And what was the denominator? 6. That's it. Right there. All right. We have 120 seconds. 3n. 3n. Yes, you can do that. But sometimes it doesn't. Which one? 3? What did you say? Factoring out something? Is that? No. No. There's no k. Remember? K's gone. Yeah. What's going to happen to n? Is n is 5 or 7? And it's going to go to where? Infinity. N is a number of intervals, right? We're not going to divide 5 or 7. We're going to divide into a zillion intervals. So n goes to where? Infinity. And it's going to go to infinity. All right. So do you see the 3 and 2 and 6 and cancel 3? What's inside there? N squared plus n. Fair enough. How about the other one? Is a 3 and 2? Good. So it's a 3, 2n squared. And here you have to distribute that as n times. If you distribute this one, 2n squared plus 3n plus 1. Then n and n just cancel. So you have 3n. Just do it. 3n plus 3n. If you distribute that, you have 3 divided by n, right? No, just 3n again. N and n cancels a 3n. And this is just 3, right? N and n cancels. Minus 3 over 2n. And if you distribute that, 3 over 2n and 2n and n cancel, so you're left with 6n. 2n, one copy of n and a copy of that. Minus, and a plus in here, if you let's do that all together, negative as well. So it's a negative, it's a 9 over 2. And if you do that, you have negative 3 over 2n. Like that. If you multiply that, time's up.